So now let's finally finish that proof from last class. So let's recall our claim was that for any, and Alex is totally right, I should say positive, for any positive 4-digit number n, 3 divides n if and only if 3 divides the sum of the digits of n. That's what we're trying to do. And remember, like for example, 3 divides 57. Since 57 equals 3 times 19, right? And also notice that 3 divides 5 plus 7, which equals 12. That's just an example. That shows there's some merit to this. 3 divides 57. It also divides the sum of the digits. Because 3 times 4 equals 12. That's why that works. But yeah. So that was what we had right there. And then to do this, we defined a set S to equal the set of 4-digit numbers. I'll say positive. Which we can more formally write as a 4-digit number is any number that has 4 digits, right? So any number that equals 10 cubed, or A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 plus A0 times 10 to the 0, such that A3, A2, A1, and A0 are all in the set 0 to 9. So all of these come from 0 to 9 because that's how digits work, right? Any digit in a number is between 0 and 9. Whole numbers are between 0 and 9. That's your set S. And so the formal way to write this claim is for all n in z positive, that's just going to be the positive integers, 3 divides n if and only if there exists, actually I'll just say S. There you go. For all n in S, 3 divides n if and only if there exists A3, A2, A1, A0, and 0, 9, such that n equals 10 cubed A3 plus 10 squared A2 plus 10 to the 1 A1 plus 10 to the 0 A0. That happens. And 3 divides A3 plus A2 plus A1 plus A0. All this is saying is that 3 divides n if and only if 3 divides the sum of the digits. This part's just telling you how to write in as like base 10, basically. All right, so our proof that way we did last time. Done. This way we'll do right now. So now, instead of starting with the, so now last time we proved this direction, which means last time we proved that if 3 divides n, 3 will divide the sum of the digits. But nowhere in that proof do we really find out that if 3 divides the sum of the digits, 3 must divide n. So now I want to go this way. So that not only does 3, if 3 divides n, 3 divides the sum of the digits, but also if 3 ever divides the sum of the digits, 3 will divide n. Does that kind of make sense, that distinction? Cool. That shows that these two things are equivalent, basically. They happen at the same times. So now we're going to start from this way. This is going to be a direct proof. So let n be an S such that there exists A3, A2, A1, A0, and 0 to 9 with n equal to A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 to the 1 plus A0. All right, we have all that. Yeah. Oh, sorry. And 3 divides A3 plus A2 plus A1 plus A0. So because we're proving this direction, right, the first thing we do is just let n be an arbitrary element, arbitrary of a particular element in S, where all this is satisfied. Where n can be written this way, which everything in S can, and 3 divides n. Or 3 divides the sum of the digits. That's the key. 3 divides this right here. So I want to prove that 3 must divide n. So what do? Well, we do the same clever thing we did last time, where we can actually use this to rewrite n in a way that's more useful. So let's note that n equals A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 to the 1 plus A0. By definition. But then 10 cubed is actually 1,000. 10 squared is actually 100. 10 to the 1 is 1. And we just have A0 here. And this is by evaluation, I'll say. Just doing 10 cubed and doing 10 squared and doing 10 and all that. Then remember the trick was 1,000 equals 999 plus 1. And 100 is 99 plus 1. And 10 is 9 plus 1. So for each of our digits here, and this is by addition, thus each of our digits here, if we distribute this out, we'll retrieve A2 times 1, A1 times 1, A3 times 1. We'll get all of our digits with some stuff left over. And stuff left over being, this is going to be 999 times A3 plus A3 plus 99 times A2 plus A2 plus 9 times A1 plus A1 plus A0. This is by distribution. And this is going to equal, if we group it together, if we group kind of this extra bit together, 999 A3 plus 99 A2 plus 9 A1, and then we have the A3 plus A2 plus A1 plus A0. So the key is by looking at it in this way, we will recover the sum of our digits right here. And now we're so close to being done. So everyone remember this, because I'm going to erase to get more room. Actually, yeah. All right. So we're still going with the proof. So pretend like I just paged down. So we have that n equal ... It was 999 999 A3 plus 99 A2 plus 9 A1 plus A3 plus A2 plus A1 plus A0, which equals, this right here is a multiple of 3, right? Because 999 is multiple of 3, 99 is, and 9 is. This 3 times 333 A3 plus 33 A2 plus 3A1. And this is by factoring. So note, 999, this is 3 times something. So this is this right here is divisible by 3. And this, by definition, is divisible by 3. So n equals something divisible by 3 plus something divisible by 3, which by our theorem means it'll be divisible by 3. That's the brilliant part here, right? The brilliant part is we rewrote in this way as something plus the sum of the integers, or the sum of the digits, and that something happens to be divisible by 3. So that's why all this works then. So note, since 3 is an integer, 3 divides 999 A3 plus 999 A2 plus 9A1 by definition. Therefore, by theorem, since 3 divides 999 A3 plus 99 A2 plus 9A1, and 3 divides A3 plus A2 plus A1 plus A0, that was by the assumption of the problem, since we're starting here and trying to get here. 3 divides n, which equals 999 A3 plus 99 A2 plus 9A1 plus A3 plus A2 plus A1 plus A0. Done. All right. Sorry for going over. Class is over. My bad. This proof always takes longer than I think it will. But the reason I want to show you guys this proof, even though it's a little more complicated, I think it's probably a little above maybe the scope of this class. Like I wouldn't probably ask them this hard on a homework just straight up, or on a test just straight up. But it shows you that just with the information we have, we can prove some kind of powerful things. This is not obvious. I mean, like you could do some examples in your head and convince yourself it works, but it's not obvious that this works for any single multiple of 3, but it does. So now, if you didn't know this rule before, right, if anyone gives you any number, you can be like a magician. If anyone gives you any number, right, you can very quickly tell them if it's divisible by 3, and you can tell them why. Although people don't usually like the why, they get mad at you. But anyway, yeah, any questions? Well, that's class. There's all leading up to this. The point is, this is a cool rule, but we don't really care with the rule. Like this will probably never come up in this class again to apply this. It's the idea behind the rule. The idea behind, oh, we can rewrite in a special way like this, and we can use what we know. We use this theorem down here. It all works together. And this is a cool example of biconditional where it goes both ways. Where 3 divides in, it divides the sum of the digits. If 3 divides the sum of the digits, it divides in. I'm talking in circles. I should quit. Okay, I'm stopping recording.